Cool, yeah, I hope everyone had a nice coffee break. So today we'll be talking about the very interesting topic of how we ship security agents in production and how we leverage guardrails along the way. So specifically, we're going to focus on two agents, a threat modeling agent and a security routing agent. So we could probably use a little bit more creativity in those names, but the core problem we're trying to solve with our security team, and maybe you've seen this in your security org as well, is too many security reviews and not enough human time, and also getting our users the answers to the questions they need efficiently. So here's our agenda for today, but very concretely, we're going to dive into the architecture of these agents, how we approached quality and measured accuracy, how we met users where they were throughout the process, and finally finish off with some learnings. And as mentioned before, Sid and I are software and security engineers at Stripe.
Yeah, so there are two main problems we try to attack using AI for security at Stripe. One of them being security routing, and what I mean by that is how do we get users, given so many different security teams, to the right one, while minimizing development time and friction for security engineers. Another problem we were trying to solve is with threat modeling, and what I mean by that is with the rise of the use of AI in the software development lifecycle, how are we attacking this increased demand for security guidance? And of course, there are a bunch of different challenges associated with creating agents for the two, but one of the main challenges we focused on was hallucinations. As we've all come to know and love, AIs can and will hallucinate. And these hallucinations can actually end up recreating the problem we're trying to solve in the first place. For example, with security routing, if we're routing people to the wrong team, then we're having to get security engineers and developers re-involved in this whole process of getting them back on track, recreating the problem.
Cool, so with that context in mind, we're going to dive into how we approach the design, starting with our threat model agent. So one important consideration we had to make in the beginning was, will this agent be more of a long-running, async process in the background, or do we need to be more conversational and faster in its response time? And that way, we could look at the trade-offs between, hey, do we want to focus on accuracy and processing rather than having to get a very fast response? And so in our case, we actually opted for the latter. You can imagine we have a security review ticket come into our queue, and our agent can take the time and processing time that it needs to get back a response. So this led us to take a modular multi-agent structure. So on the right, you can see that we have an orchestrator agent, which has a couple parameters it takes in based on our intake form, for example, a security review category. It then feeds it into input agents, relevant security agents, and then lastly, our output agents. So our input agents, the main goal is to get the relevant additional input context that come in your tickets. Sometimes there are Google Doc links, Slack threads, additional information that's relevant that we want to include for our security agents. And with our security agents, we try to take a very specialized, targeted approach. And so what I mean by that is, imagine we have a third-party security review agent. We wanted to make sure that it was specific to that category. And when we're balancing determinism versus non-determinism, we believe that there was a core baseline of required questions that was required to make any third-party security review complete. Things such as what's the data sensitivity involved, what's the data transport protocols, what's the auth story there. And so this doesn't necessarily limit what the agent could review, but it had to at least include information on these points to get a complete successful threat model. The other decision that we made was to be very intentional with the tools that we used. And so one that I'll explicitly call out is having great internal guidance tools. LLMs are good at giving more generic security context, but what's really powerful is having company-specific guidance that aims to provide risks and mitigations that can be actionable. And then lastly, these are fed to our output agents, and we'll talk about this a bit more later on, but you can imagine there's different audiences that want different formats. Now, why did we take this more sequential agent approach? And the reason behind that is we wanted more predictable behavior for certain areas. We always want the input agent to run first, security agents to do analysis in parallel, and then lastly our output agents to run. We found that when we gave our orchestrator agent too much agency, it wouldn't always run the relevant specialized agent that we wanted it to. Now, this doesn't mean we're stuck with this sequential approach. We're thinking of doing a more hybrid one where, similar to how we approach the core baseline, maybe we have a core baseline of security agents we need to run based on human input, But if it's a very vague category, we want to layer on top agency from the orchestrator agent to say, hey, maybe a web specialized agent is applicable here.
Yeah, so for the security routing agent, we decided to take a different approach instead of the sequential agent structure, especially given the fact that any question could be dealt with for security routing. So instead of using a more sequential structure, initially we started with a one-step LLM call, give it no access to tools, no access to the internet or anything local at Stripe. Instead, we just started with a simple prompt that had a bunch of pre-contextual information about the various security teams at Stripe. And while this ran really fast, you can see that it probably didn't work for a lot of reasons. One of the main ones being that it's not going to know about any internal terms or documentation used at Stripe. So if the user's question was relating to any software development that was using any of those internal tools, terms, et cetera, the AI would often hallucinate. We then decided to shift to a more agentic structure, giving it access to tools to compile its own set of information. So we took this one-step prompt, took out all this contextual information about the various security teams, and instead encouraged it to research on its own. At the beginning, we provided it with as many tools as we could to just get a complete picture. And this worked great for accuracy reasons, but for performance reasons, the agent took around 10 minutes to run, hardly conversational at all. So to get it down further, what we decided to do is try to get the tool set down specifically to be as minimum and as concise as possible. Through a slow and iterative process of just taking a set of baseline questions we knew the answer to, testing the agent, plucking tools one by one, retesting the accuracy and ensuring it's not changing too much, we were able to get down to about 2 tools and a runtime of around 30 seconds.
Great. So, with all this discussion around our agent architecture, how did we know that was the right choice? And if it was the right choice, that when we make changes, that they're actually improving the agent? So starting with threat modeling, as many of you may know, threat modeling is often more of an art than a science. And there's not a single right answer, right? There's not a single right threat model. So when we're looking into different ways to score the threat modeling, we were first approached with, hey, can we do deterministic matching? And this didn't really fit the bill. When we tried to compare MITRE categories, we found that there would sometimes be wrong labeling. The agent would have the correct risk, but in 2 different runs, it would label them as one category and another time in another category, even though the risk itself was being communicated correctly. Other more simpler methods like keyword matching didn't fit right as well. So this made us turn to what really matters. And what really mattered was the semantics and meaning behind the risk being conveyed. And so we turned to LLM as a judge. Now, one question that comes up with LLM as a judge is, do we trust the LLM to evaluate the threat model in isolation? And it's a bit of a cyclical dependency because the whole reason why we're doing this evaluation is because we don't trust the LLM to give us a 100% correct threat model, right? So why are we going to allow the LLM to evaluate and trust that it'll give us 100% correct evaluation? So to address this and take a more balanced approach, we wanted to have humans involved and take advantage of what humans are good at in creating golden standard-based test cases, right, based on past security reviews, and also what LLMs are good at, which is semantic reasoning. And so in this flow, what we tasked the LLM with doing is, hey, given this expected output on our golden standard test case, what are the semantic equivalences between that and our actual output from our agent, right? So looking at the risks, the mitigations based on semantic equivalence. And we felt like this was the right approach to get to the right meaning behind the risk. And so at the bottom, you can see how that sort of looks in our iteration model, where we have a golden standard test case with its corresponding actual agent output. And we would iterate on that based on the scoring accuracy to get to an accuracy that we were happy with that improved the agent before sending out our pull request in the offline mode.
Yeah, so with this evaluation pipeline in place, how exactly did we take advantage of it? Well, we first started and looked at our base prompt and found that there are a few test cases within our golden set that were particularly low. We use these test cases to guide improvements in our prompt, not specifically by overfitting it, but just by encouraging the prompt to act more like a security engineer. For example, one of the specific things we did was by giving the prompt specific security domains to always consider, such as authorization and single sign-on. This guided improvements to get us about 10% increase in accuracy. One of the other things we used the eval pipeline for was to select the best flagship LLM model for our threat modeling agent. Specifically, we did this by creating a mega data set using individual copies of our golden set standard cases. The reason we duplicated our test cases was to really eliminate the non-deterministic nature of AI between runs. By using this simple process, we were able to test and automate testing each baseline LLM model and swap it with the one that performed the highest. This led to another increase of about 10% in accuracy. But finally, one of the largest impacts from this evaluation pipeline is the fact that it really gave us confidence in the changes we made to our prompt. For example, take a look at the prompt you see on your right where it says you're a security engineer and then describes how to properly format a JSON. On an individual run without the evaluation pipeline, things might look great. We're outputting a correctly formatted JSON threat model, and we're also giving security advice. But what the eval pipeline is actually showing us is that overall accuracy has gone down 10% because the agent is focusing more on how to properly output a JSON and less on actually providing accurate security guidance. So this eval pipeline really gives us confidence in the changes that we make to our prompt, in the sense that they're applying generally speaking, rather than just in minute cases. Yeah, so the eval pipeline for security routing was a bit different. It relied more on user-provided feedback, given the open-ended nature of the situation. Instead, we relied on releasing to a small bubble of users, iterating on user feedback, increasing that bubble, and so forth. Specifically, we started by releasing the agent just to be accessible via a web page, just so that our team members and anyone across Stripe internally could access it. Then, taking this feedback and getting more confidence in it, we wanted to test how it handles user situations. So we made it invocable in Slack to really test context dependence. Finally, after iterating on that phase, getting confidence in it, we released it to all developers across Stripe in the internal chat UI for agents at Stripe. This was really to meet developers where they are. And then, of course, we also relied on demos and outreach to, again, just get as much feedback as possible from direct users, again, given the open-ended nature of security routing.
Cool. So speaking about meeting users where they are, we want to highlight a couple of key actions that we took as a team to make sure that users were kept involved in the process. So the first one is phase rollout. So this one we'll be talking about in the threat modeling context, where we chose a specific subcategory of security reviews that we believed agents would be able to perform well at. And what that means is choosing security reviews that had very similar risks and very similar mitigations. And we believe this more constrained domain made it better for an automation setting. Once we had our established subcategories of security reviews, we built out our agent architecture and ran this all in shadow mode. During this process, we continually iterated using our evaluation pipeline discussed before to get to an accuracy that we were confident in. Now, you might ask, how do we determine what accuracy threshold? And I think this really depends on the behavior of your agent. You can imagine if your agent is directly sending these threat models, these risks, and making super noisy integrations into your engineering teams, if you don't have a very high accuracy, you're going to get a lot of slack. Those engineering teams are not going to be happy. Versus if we add in a human in the loop where maybe the agent gets you 90% of the way there, right? But you still have that one last step of a human confirming those threats and mitigations are applicable, we can go for slightly less accuracy. So we ended up with the latter approach, aiming for around 80% in the beginning and then continuing to iterate on it once it became visible to our users. Now, speaking about our consumption methods, while the semantics first risk representation was great for our evaluation model, we found that other audiences wanted different formats. For example, humans wanted a more summarized format, while we had threat modeling tool that wanted more structured format for metrics. So we opted for a MITRE framework there. And then lastly, we recognized that the threat modeling agent doesn't always output something that's fully complete, right? Especially for more vague categories, we want to have the option to continue the conversation in our conversational agent. And the focus here was making sure that the input going to the conversational agent had the necessary context and almost proof of work from our threat modeling agent to make it successful. Then lastly, we recognized that we're not always operating with perfect information. And when we're missing information, we shouldn't have the expectation that threat model should be 100% complete, right? The threat model agent should call out where the missing information is, that the status is unknown, and set the security engineers up to, bring up to the next step, which is, hey, based on this question, if we can answer it, we can tell if this risk is mitigated or it's not.
Yeah, so there are a lot of great learnings we took away from this whole process, one of them being about Alpha Evolve. If you don't know what Alpha Evolve is, it's this Google AI DeepMind LLM tool that essentially evolves algorithms, or in this case, prompts, using a process similar to natural evolution. So in this case, let's work on an example. We take our base prompt, we make a bunch of different variations to it, adding a few words here, maybe changing the wording here, and then take the one that performs the best, a score through our evaluation pipeline and take it to the next round. We repeat this process until we get the truly most evolved form of the prompt. While this sounds great in theory and works great in a lot of computational and mathematical cases where there are only so many permutations of things you can try, in the case of language, because of how open-ended it is, we found that it didn't really work great, especially within the realms of the cost we were able to handle. For example, in this case, all it did in variation 1 was add 2 words, not really semantically changing the prompt at all. In the second variation, it just paraphrased the entire prompt. Again, not adding any semantic changes that would actually hopefully guide improvements. So in this case, we found out that alpha evolve didn't really work great. Another learning we had is that we found out that humans in the loop aren't optional, and this really goes great with what Jeffrey's been talking about in the sense that we have all these LLM-generated threat models and a relative amount of confidence in it, but because we don't have that full confidence, we don't want to actually act on these results. We want a security engineer to still review these AI-generated threat models and push forward threats that are actually relevant, and of course deny those that aren't. Another learning we had goes back to the JSON example, which is investing in your eval pipeline early. And what I mean by that specifically is that if we had just not invested in our eval pipeline early and instead focused on just getting those edge cases correct, and et cetera, we would have ended up with some big garbage mess of a prompt that maybe scores great in some very weird cases, but generally speaking, focuses too heavily on specifics, and generally performance will go down. Another learning we had is that agent architecture really depends on the task. We saw that a multi-step child agent architecture worked great for the threat modeling agent, but the security routing agent, a more simplistic, undetermined structure really worked. There's not really a one-size-fits-all here. And then finally, one of the most important learnings we had is that garbage input really means garbage output. And of course, we don't want our threat model agent to produce garbage output. We want it to handle all threat models like a security engineer would. Take this example, garbage input ticket, where there's not many specifics at all. Initially, our LLM would end up hallucinating information, saying things like encryption and rotation, things that aren't mentioned in the ticket at all. We had to teach it to act more like a security engineer, be okay with saying, I don't know, and that there's not enough information, rather than, of course, hallucinating this information to produce good output.
Great. Yeah, that's the end of our talk. Thank you guys for listening.
Let's do some questions. I see Shruti.
Hi, thanks for the talk. I was curious if accuracy was the only metric that you used in your evals, or did you try other metrics as well?
So you said if accuracy was the only metric?
Or did you try other metrics for scoring in your evals as well?
Yeah, I think, so specifically we used the offline accuracy one, where it was, before the threat model or changes to the threat model agent were released, we would base off of that. In the next iteration, and this is something we're trying to build out, is to give more online evaluation, right? So when a threat model is done on a new security review, how would it perform? And the way we're thinking of approaching this is, traditionally, if it's a human grading it, that's great and all, but that involves more security process. You would need all the humans to do it, and that's not always guaranteed. So what we're trying to integrate is to have our security threat model tool that we mentioned earlier as sort of the source of truth. And our threat model agent would generate, hey, these are the threats that we found, and users would use that as a source of truth to click approve, sort of deny, and utilize those metrics to give more of an online feedback loop, and that would provide more accuracy. So we're looking at from both approaches.
One question I had was, have you guys looked into Maestro framework and leveraging that as well as part of, because I think the Maestro framework is specifically for AI scenarios. It's a threat modeling framework, Maestro.
Sorry, can you repeat that one more time?
I'm wondering if you took into account or are thinking about Maestro threat modeling framework into account?
So the Maestro threat modeling framework. I think that could be something we build out in the future. I think for now, just building on our existing processes, most of it has been in the MITRE format. But I think that format could go well based on what sort of risk and security views we're seeing, where it could be more applicable.
You said that you saw a 10% reduction in accuracy in the threat models coming out of that. Did I understand that correctly?
Could you repeat the question? Sorry.
You said that you saw a 10% reduction in accuracy in the threat models that were being generated through this. Did I hear that correctly?
The threat models that were being generated through
Through this path.
Oh.
You said I saw a 10% reduction in accuracy. I'm curious, what level of accuracy are you actually looking to achieve before you put it into production?
Oh, I thought they were talking about the JSON formatting that led to the 10% reduction.
the hyper.
Okay, I
Right?
misunderstood.
Okay,
Thank you.
maybe we'll come back afterwards and
sorry.
we can answer that.